All right, so here we are, Kinesiology 230, still chapter 3. Presentation number 3, we're going to build off of the ATP conversation we had earlier, and then we're also going to talk a little bit more about the phosphagen system. You may recall there were 3 energy systems in the body. One was the phosphagen system, and that was about all short-term explosive type activities. Let me get my face out of the way. And when you look at uh, energy is stored in the chemical bonds of ATP. It's used to power muscular activity. The replenishment of ATP in human skeletal muscle is accomplished by 3 basic energy systems: a phosphagen, glycolytic, and oxidative. For this presentation, we're talking about the phosphagen system. And with that, the term itself comes from Greek etymology. It's phospho, meaning phosphorus, and then gen, meaning producing, generating, like Genesis, if you will. And then you have a high energy bond that stores and releases energy when broken. So when we go from adenosine triphosphate to adenosine diphosphate, we're breaking a bond, we're losing a phosphate, and we know that's a catabolic reaction because we're breaking a bond and we're gaining energy. So as we saw before, the ATP itself has these 3 high energy bonds, and we're constantly going through a process of catabolic to anabolic, anabolic to catabolic as we're putting the building blocks together or breaking them up to store energy or to release energy. If you want, you can click here in the presentation itself. That will take you right out to a link out to a search I did in terms of what the heck is phosphagen, where does it come from, etc. All right, jumping into this. Just a refresh, we have the adenine and the ribose. They come together to give us the adenosine. And we know that adenine is a nitrogen-containing base. And then when you look at ribose is a 5-carbon sugar. You have 1, 2, 3, 4, 5 carbons right there. And then the adenine plus the ribose give us our adenosine. So that's one part of adenosine triphosphate. You have these 3 phosphate groups. They come together, and they're held together with a phosphorus atom and 4 oxygen atoms. And the 4th oxygen atom is actually shared with the previous phosphate group, right? So these guys come together, and this last one reaches back into the adenosine for its last oxygen. And it's these bonds in here that get broken and cause the release of one of the phosphates to give us energy. Catabolic reaction. I'm going to say it 1,000 times. I'm going to get myself out of the way here. So, the phosphagen system, it's a primary source of ATP. If you remember back to the tiles that were up on the screen, you had the thrower, then you had the 800-meter runners, maybe the 400-meter runners, and then you had long-distance runners. These are the people who are like the throwers, the pole vaulters, the jumpers, a very explosive type of activity, kind of a one and done, maybe sprinting for 10 seconds and that's it. But as I mentioned, all energy systems are upregulated and downregulated throughout any activity. It's just to what degree and what is the predominant source of what's the predominant energy system that's providing the energy. And with the phosphagen system, whether it's the thrower or was the young ladies running the 5K for cross country or 3K, whatever it is for cross country for high school, it's active at the beginning regardless of the intensity of work. And this system relies on chemical reactions of ATP and creatine phosphate. And you'll see ATP CP or ATP, sometimes PC, phosphocreatine written. But I want to point this out to the right. The energy system relies on the chemical reactions of ATP and creatine phosphate. And I mentioned it before in the other slide in terms of, phosphorus. Where does that terminology come from? But the other thing you'll see is ATPase, creatine kinase, ASE. And I would urge you to go out and maybe do a little research on this because these are the guys that actually do the heavy lifting, so to speak, when it comes to the electron transport process. And we'll talk more about it. But both, when you look at it, ATP and creatine phosphate are both phosphagens, and you can kind of deduce that from adenosine triphosphate and then creatine phosphate are both phosphagens, right? Pretty easy to put that math together. That involves enzymes, myosin adenosine triphosphate, or commonly known as ATPase, and creatine kinase, which is, again, if you look at those 2 words and how closely related they are, it's one of those where it's kind of 400 level stuff, but you can still take a look at our 200 level course and kind of start to research that. So myosin ATPase, it increases the rate of breakdown of ATP to form ADP, an inorganic phosphate, and releases energy, all of which is a catabolic reaction, which we know. Creatine kinase increases the rate of synthesis of ATP from creatine phosphate and ADP by supplying a phosphate group that combines with ADP to form ATP, which is an anabolic reaction. So if you look at this and kind of parse it out, you have, as I mentioned before, this constant catabolic, anabolic back and forth that happens in our body. We're doing, we have a catabolic reaction where we're cutting up or we break off one of the phosphate groups from ATP, right? Adenosine triphosphate. That is catabolic. Meanwhile, when you look at this, creatine kinase increases the rate of synthesis from creatine phosphate and ADP by supplying a phosphate group that combines with ATP to form ATP, which is an anabolic reaction. So notice what's happening here. You have these different either kinase or ACE that are involved in a process that either bring us another phosphate or break a phosphate and carry that through the electron transport system. So I would urge you to read this paragraph maybe 7 or 8 times and really wrap yourself around this whole concept of how when you have myosin ATPase, it increases the rate of breakdown of ATP. So we're going from ATP to ADP. So we're going from triphosphate to diphosphate. You know that that's catabolic and we're releasing energy. Creatine kinase increases the rate of synthesis of ATP from a creatine phosphate and ADP. So we have adenosine diphosphate and a creatine phosphate that come together to give us ATP, which is an anabolic reaction. Again, there's so much that goes into this, but it's a lot of back and forth in terms of catabolic, anabolic, anabolic, catabolic. We're breaking things apart to get energy. We're putting them back together to store energy, however you want to visualize it. So I put this back up here again, so you can just kind of wrap yourself around what we were just talking about in terms of breaking these energy bonds. And you have this kind of catabolic reaction where you end up with an adenosine diphosphate. The phosphate comes back into the picture. You end up with 3 inorganic phosphates. That becomes an anabolic reaction. Catabolic, breaking it off, anabolic. Notice you have ATPase involved in the process, which allows that to happen. That's the ATPase that we're talking about in here. Myosin adenosine triphosphate. That's what happens in this diagram. If I get myself all the way again, in here, as we go back and forth between adenosine triphosphate and adenosine diphosphate. Ebb and flow, back and forth, catabolic, anabolic. That's all it is. Bring myself down here. So the phosphocreatine system provides energy at a high rate, but it doesn't provide energy for long duration kind of continuous activities. That's more reserved for the oxidative side. So the limiting factor, it's a small amount of ATP and phosphate that's actually stored in the muscle itself, and this system doesn't generate large amounts of ATP. And you generally see this in the type 2 muscle fibers, that are very explosive in nature, very kind of like short-term explosive activity driven. And what you'll see is the type 2 muscle fibers contain a greater concentration of phosphagens than type 1 because they just don't work on the oxidative side of the house. So creatine kinase, it regulates the breakdown of creatine phosphate, and an increase in muscle cell concentration of ADP promotes creatine kinase activity. And I'm going to pause you right there. Just think about that. If you have an increase in the muscle cell concentration of adenosine diphosphate, what you have is you have a bunch of adenosine triphosphate molecules that gave up one of their phosphates to release energy. You have a series of catabolic reactions to give us the energy. And then you have a bunch of ADP sitting around. A bunch of ADP sitting around needs one thing. It needs phosphate. And so what happens is you have creatine kinase. You have this process where the creatine kinase then breaks down the actual creatine phosphate. And as we read through this paragraph a little bit further, an increase in ATP concentration inhibits it. So think of this, just think of what's going on. If there's plenty of ATP in the muscle to perform a contraction, you don't need an increase of phosphate. So when you look at creatine kinase creatine kinase activity primarily regulates the breakdown of creatine phosphate. Got it. An increase in the muscle cell concentration of ADP promotes creatine kinase activity, right? So that enzyme kicks into action as a result, because you end up having a bunch of ADP that needs another phosphate molecule to be able to become ATP. If you have a bunch of ATP, then you don't really need the increase of phosphate in the muscle. So you don't have this creatine kinase activity itself, right? So it's this kind of, I always describe it as like the phone that calls the ATP factory. Hey, we need more ATP or we need more phosphate. That's kind of the phone line, if you will, to the factory. So at the beginning of any exercise, ATP is broken down into ADP and it releases energy from muscular actions. We know this. And the increase in ADP concentration activates the creatine kinase. That's the phone call that goes to the factory to say, hey, make more phosphates so we can create more ATP. And it's just, that's the mechanism, right? So the breakdown of creatine kinase actively remains elevated if exercise continues at a high intensity. If exercise is discontinued or continues at an intensity low enough to allow glycolysis or the oxidative system to supply an adequate amount of ATP for the muscle cell's energy demands, the muscle cell concentration of ATP will likely increase. This increase in ATP results in a decrease in creatine kinase activity. As that ATP goes up, you're going to have a decrease in the creatine kinase activity. Notice kinase, ASE, yet again. And so what happens if there's ADP? Meaning you have ATP drops, ATP levels drop, and you have higher ADP levels. Well, the result of that is you're going to see an increase in creatine kinase activity. That enzyme is going to come and be called to action to help create the phosphate that we need to be able to have ATP to be able to have muscular contraction. Again, it's a constant ebb and flow, guys. I'm going to break off from there and move on to the next one.